Hello, today we're continuing in our A-level physics revision series and indeed continuing to look at fluid dynamics, but now we're going to look at what is called Bernoullis theorem or Bernoullis equation. Bernoullis equation relates to the movement of a fluid through a pipe. I'm going to take a pipe which looks like this, and you'll notice two features about this pipe. The first is that the fluid is coming in here and it's coming out here. You'll notice that the area of the pipe at this point, which we will call A1, is much greater than the area of the pipe at this point, which we will call A2. You'll also notice that the pipe has gone uphill, and so we will call the height of the pipe above some sort of ground level H1 here and H2 here. You don't need to worry too much about the fact that the pipe has a physical height. We are assuming that the height, as it were, of the pipe is much greater than, although my diagram doesn't suggest this, than the height above some fixed point. So we don't have to worry about the fact that there is a height associated with the width of the pipe. Now, the first thing I hope you'll all agree is that the volume in, as the fluid goes in, must equal the volume out. That's the fluid coming out. You can't put more in than you get out, and you can't get more out than you put in. If you put in a gallon in this direction, a gallon has got to come out in that direction. Now let's suppose that the fluid is moving in at a speed or velocity of v1 meters per second into the pipe, and it's coming out at a speed of v2 meters per second out of the pipe. The question is, how much fluid goes in 1 second? Well, in 1 second we've got v1 meters times an area of A1. So essentially we've got a cylinder of fluid. In 1 second the V1 meters of fluid will flow in, and it will have a cross-sectional area of A. So the volume that is flowing in 1 second will be V1, which is the velocity, times A1, which is the cross-sectional area. What is the volume flowing out? Well, the volume flowing out in 1 second will be V2, is the number of meters that will flow out, times the cross-sectional area A2. So the volume flowing out is V2, the velocity flowing out, times A2, the cross-sectional area. But we just said that volume in is volume out, so those two must be the same. And that means we can say that V1 over V2 is equal to A2 over A1. And if A2 is less than A1, which of course it is, then V1 is less than V2. So the speed coming in is going to be smaller than the speed coming out. And you can do this yourself by taking a hose pipe. If you make the exit of the hose pipe thinner, then the water will come out faster. So slow water going in because it's got a large cross-sectional area to get in, but because the cross-sectional area gets smaller, the speed will increase as it comes out. Now let's think about the energy. Total energy is the kinetic energy plus the potential energy. And that is usually written as half mv squared, that's the kinetic energy, plus the potential energy, mgh. And that can be simplified as m into v squared over 2, that's the kinetic energy part, plus gh, all inside the bracket. Mass is always, of course, volume times density. And so we can now say that the energy at the entrance to the pipe, which we call E1, is equal to the mass, which is the volume, times the density. Well, the volume, of course, is A1 times V1 per second times the density rho into V1 squared divided by 2 plus G H1, because it's H1 and it's V1 is the velocity. The energy coming out, E2, is going to be the mass, which is the volume times the density. Well, the volume now per second is going to be V2 times A2. So this is A2 times V2, incidentally that should be V1 of course, times is same fluid, so the density remains the same, into V2 squared over 2 plus GH2, where H2 is now this height. And the difference in energy, which we will call delta E, which equals E2 minus E1, is the work done to get that fluid to go uphill. So if we think about the exit and the exits, the entrance and the exits of the pipes, the pipe of course goes like this. There will be a force in, call that force 1, and there will be a force out, we'll call that F2, and the work that is done is equal to the force in, the work in, which is force times distance, minus the work out, which is force times distance. And force is pressure times area. So that is equal to pressure 1 times area 1 times x1 minus pressure 2, area 2 times x2. And that equals E2 minus E1, because we've said that the work done is the energy 2 minus the energy at point 1. Now in 1 second, the distance is of course going to be the equivalent of the velocity. So you can put V1 here and V2 here, because that is the effect of the distance for every second that the fluid is travelling at velocity V1 or V2. And the values for E2 and E1 were calculated here, E2 and E1. So I'm just going to write down what E2 minus E1 is using those terms. It's rather long-winded, but bear with me. For E2, we have V2 times A2 times rho into V2 squared over 2 plus GH2. That is E2. And now we minus or subtract from that E1, which is V1 A1 rho into V1 squared over 2 minus GH1. And that is E2 minus E1. And that is equal to that. Now if we rearrange this equation to bring P1 A1 X1 plus that term equals P2 A2 X2 plus that term. So we get P1 A1 X1, which is of course now V1, that's here, plus this term here, plus V1 A1 rho into V1 squared over 2 minus that should be plus GH1, plus GH1 is equal to this term here, P2 A2 V2, because X2 and V2 are the same if it's per second, plus this term here, V2 A2 rho into, can I squeeze it in, V2 squared over 2 plus GH2. Let me just move it across a bit so that you get a chance to see it. There we are. Now that looks absolutely awful, But we can simplify it because we know that volume in is volume out, which means that A1 V1 equals A2 V2. And if you look, you've got that common throughout. A1 V1 there, A1 V1 there, A2 V2 there, A2 V2 there. All of those cancel out. And that leaves us with P1 plus rho into V1 squared over 2 plus GH1 equals P2 plus rho into V2 squared over 2 plus GH2. Which means, and this is Bernoullis Principle, that at any point in the fluid, the pressure plus the density into V squared over 2 plus GH is a constant. Finally, I want to touch on Stokes Law, which relates to viscosity. Viscosity can be thought of as the stickiness of a fluid. Think of water, think of treacle. Treacle is a good deal more sticky. If you had to move your hand through water, you could do so much more easily than if you run your hand through treacle. There would be more resistance to movement in treacle. So let's take a container with a fluid in it and let's make it treacle. And what we're going to do is to take a ball bearing of radius r, and we're going to drop the ball bearing down into the treacle so that the ball bearing falls through the treacle. And we're going to measure it falling through a distance d. And we're going to time it to find out how long it takes to travel that distance. And if we time it, we shall be able to deduce its velocity because we know the distance and we know the time. And Stokes said that the force is equal to 6 pi times eta, which is the viscosity of the fluid, times r, which is the radius of the ball bearing, times v, which is the velocity of the ball bearing as it flows through, or as it goes through the fluid. The force is known as the viscous drag. It's essentially the degree of resistance that the fluid puts on the object that is trying to travel through it. And there are several experiments that you can do with this. You can, for example, take ball bearings of different radius and drop them through the treacle. And you will find obviously that 6 and pi remain the same. The viscosity of the fluid remains the same. The radius, of course, has changed, and so you would expect the velocity to change. And that gives you an indication of the extent of which you get a viscous drag depending on the size of the object that's going through. You can also do an experiment whereby you warm up the treacle so it becomes hotter. And then you do exactly the same experiment with the ball bearings. And what you find is that the ball bearings will travel faster through the treacle as it gets hotter, which means the viscosity of the treacle will decrease as the temperature increases. So the force, the viscous drag, will also decrease, and the ball bearings can more easily flow through the treacle when it's warmer, associated with the width of the pipe. Now, the first thing I hope you'll all agree is that the volume in, as the fluid goes in, must equal the volume out. That's the fluid coming out. You can't put more in than you get out, and you can't get more out than you put in. If you put in a gallon in this direction, a gallon greater than the area of the pipe at this point, which we will call A2. You'll also notice that the pipe has gone uphill. And so we will call the height of the pipe above some sort of ground level H1 here and H2. Hello, today we're continuing in our A-level physics revision series and indeed continuing to look at fluid dynamics, but now we're going to look at what is called Bernoullis theorem or Bernoullis equation. Bernoullis equation relates to the movement of a fluid through a pipe. I'm going to take you here. You don't need to worry too much about the fact that the pipe has a physical height. We are assuming that the height, as it were, of the pipe is much greater than, although my diagram doesn't suggest this, than the height above some fixed point. So we don't have to worry about the fact that there is a height, a pipe which looks like this. And you'll notice two features about this pipe. The first is that the fluid is coming in here and it's coming out here. You'll notice that the area of the pipe at this point, which we will call A1, is much greater